Now that you have a foundational understanding of what cryptography is, let's take a look at some of the common ciphers and cipher categories that are currently being used throughout the world. Now, this lecture isn't designed to go in depth on the mathematical functions that make encryption work, but it will give you a broad understanding of how the ciphers compare to each other and the areas in which they are used. A block cipher is a type of encryption algorithm that encrypts data blocks, which is a grouping of bits and bytes, one block at a time, and continues to encrypt each succeeding block until the entire set of data is secured. Now, this type of cipher is used much more frequently in encryption than the stream cipher that we will discuss on the next slide. Block ciphers take up more memory than other cipher algorithms because each block has to be stored before it's encrypted, and this also causes the operation to be slightly slower than other cipher systems. This isn't to say that it is incredibly slow or a resource hog, because it's actually quite effective, but in comparison to a stream cipher, block operations are a tad bit slower. Block ciphers are best used when the size of the data that is going to be encrypted is already known. So, for example, if you have 200 gigabyte hard drive that needs to be encrypted, a block cipher is a good choice because the size is known. A stream cipher is not the exact opposite of a block cipher, but its primary operation is pretty close to opposite. Stream ciphers encrypt data one bit at a time instead of waiting for a collection of bits to encrypt all together. Now, this does have some advantages in that it doesn't require as much memory since data isn't being stored before encryption, and it runs a little faster than block encryption for the same reason. The stream ciphers are not only designed for streaming media, so don't let the name confuse you. It actually stands for key stream, which is a string of bits that gets combined with some plain text to generate the ciphertext, though you do see stream ciphers in use in streaming media. Now, outside of traditional computing, stream ciphers are often seen in radio communications and are common in military applications. And the encryption that protects your wireless internet connection also uses a stream cipher. Now, your textbook provides the technical explanation of how both of these ciphers work, so we won't dig into that here. Some of the more famous block ciphers are AES and triple DES, also known as triple DES. AES is the de facto standard for encryption and is used by many of the common applications that you use on a regular basis. It can be found in secure web traffic while you make your purchases at online websites, manage your bank accounts and investments, or much of the other internet traffic that uses the HTTPS protocol. AES is also often used to encrypt data at rest on hard drives and in smartphones. The latest version of the iPhone implements AES, and it is believed that the Android implementation does as well. Some other software applications, such as TrueCrypt, also use AES as one of the options for encrypting data. AES was the replacement for the original DES encryption, but triple DES came out a few years before, and it was significantly better than the original DES. So triple DES is still considered an approved standard in government and industry, but it isn't used as widely as AES. Triple DES can be found in some email applications. Microsoft still uses it pretty heavily in its Office 365 solution, and it can also be found in the banking industry. But they tend to be a little tight-lipped about exactly what they are doing, for obvious reasons. I think long-term we will continue to see AES as a standard, and at some point in the next decade, users of triple DES will likely convert over to AES unless a new standard is developed that is even stronger. Ultimately, the strength of encryption today is based on the computing power available to try to break the algorithm. And unless a major breakthrough occurs, AES is likely to stay on top of the encryption list for a long time to come. Now, one important variable when we talk about encryption is the speed factor. Encryption is great, but if it takes 3 weeks to encrypt a few files, very few people will actually use it. We haven't discussed all of the encryption standards on this slide, but it does provide a great comparison of some of what we have already discussed. You can clearly see that AES can encrypt data almost 10 times as fast as triple DES, but you also may notice that the stream ciphers are even faster than AES. So that may make you think that it's better to use stream ciphers over a block cipher, as we already discussed that stream ciphers are faster than block ciphers. But this is not an apples to apples comparison, and the speed variable is only one of the variables that you need to consider. AES 256 is even a tad bit slower at 80 megabits per second. So we can also see that as the encryption strength increases, the speed at which it operates decreases. And that makes perfect sense because more work is being done. At any rate, this gives you a visual snapshot of what is possible. We talked about history in an earlier lecture, and I want to dial back to that here for just a minute to look at the timelines for when some of these encryption capabilities were created and how they changed over the years. The DES algorithm has been around since the early 1970s, so it probably isn't a surprise that it was broken almost 30 years later. A 30-year run for an encryption standard isn't bad at all, and when they created triple DES in 1998, it essentially just stacked the DES method on top of itself a few times to increase its strength. Technically, it is still breakable today, and NIST considers that it has a true strength of about 80 bits. But the technology needed to break it quickly doesn't really exist, so it is expected that triple DES will hang on for about another decade before it is finally put to rest. The AES implementation is a little more interesting. A challenge was put forth by NIST, which ultimately led to 5 finalists. One of those 5, known as Twofish, is actually considered stronger than the algorithm ultimately selected to be the advanced encryption standard, but Twofish wasn't selected because it wasn't as efficient. Twofish is still available for use today, and some people actually use it in conjunction with AES to make their encrypted devices even more secure. It's not unheard of to encrypt with AES and then re-encrypt those encrypted contents with Twofish. It takes a little more time, but the added security may be worth it. The funny thing about AES is that it was created by a few guys in Belgium, and once adopted by the US government, it became illegal to export any software outside the United States that used the AES standard. I remember being stationed overseas at the time, and I was unable to download a version of the Internet Explorer browser that used the 128-bit AES because of this rule. So the guys who created the algorithm couldn't even download the software that was using the algorithm. Just a bit of comical history for you. Now I want to leave you with this final image that shows a basic flowchart of how encryption works. It actually seems quite simple when viewed from this perspective, and even though this shows an example of a block cipher, a stream cipher would essentially flow in the same way. The clear text is handed off to an application that encrypts it and returns the encrypted data. Now, this loop continues for each block or bit until the entire file of communication stream has been processed. It's a little oversimplified, but it should help you as you read through the textbook to not get too confused. Now, a major takeaway here is that even really strong encryption, such as AES, is only as strong as the way it is implemented. Think about this. Passwords or passphrases are used to create the keys that encrypt the information. So if someone uses a weak password, the encryption won't be very secure. I don't have to break the implementation of the encryption algorithm if I can simply guess your password. The FBI investigation of the attack in California in 2016 involved an encrypted iPhone that needed to be broken into, and ultimately the way they got in was by brute forcing the PIN code used to protect the phone. The investigators said it took a little less than 30 minutes to gain access once they had the correct tools available. If the criminal had used a strong password, the FBI may never have been able to gain access, so we see that the encryption actually was worthless, since the PIN code was so easy to break. Anything I use encryption for uses a passphrase of typically one sentence long worth of content. Guessing or brute forcing something like that is a virtual impossibility, and it's a great practice to get into.